Hey guys, welcome back to the Kubernetes series. In the introduction to the Kubernetes chapter, we have discussed various features of Kubernetes. In this chapter, we will be discussing how we can achieve self-healing, high availability, rollout and rollback in Kubernetes with complete hands-on. So without any further delay, let's get started. In the previous chapter of this series, we created a pod. What happens if that pod goes down? Users cannot access our application. But in production, we must make sure our application is highly available. To achieve this, we should create multiple instances of our application instead of relying on a single instance. In that case, even if one instance goes down, the other pod can still serve the request. These instances are called replicas in Kubernetes. Each instance is a pod. If we create multiple pods manually, it can be time consuming and tedious. Instead of creating these replicas manually, we can automate creating these replicas with the ReplicaSet object in Kubernetes. Also, when the pod goes down, automatically bringing it back is called self-healing. When we ask ReplicaSet to create two replicas, it makes sure that two replicas are available all the time. If any replica goes down, it will create a new replica immediately. If an extra replica is created, it will delete a new replica. Perfect. Now we have multiple instances of our application running on a node. What if this node goes down? Again, the same problem. Users cannot access our application. To make our application available, we should bring all these pods onto a healthy node. The same replica set can do that job for us. Let's see that in action. Now I am on VS Code and I am going to create a new file called nginx-replicaset.yaml. As we discussed in the last chapter, these attributes are mandatory for any Kubernetes spec file: API version, kind, metadata, and spec. We can get the API version of the replica set with kubectl API resources grep replica set. So this is the API version and RS is the short name for the replica set and replica set is the kind. So let's go back and fill these fields. app/v1 kind is the replica set. Let's give the name in the metadata section nginx-replica set. We can give labels as well, but I'm skipping for now. In the spec, we should give how many replicas we should have for our pod. Let's give it as 3. Replicas as 3. Here we are mentioning replica set to create 3 pods. Well, what pods it should create? That we should give in the template section. Template. This spec is same as the spec we defined in the pod. So let's open the pod specification and copy everything and just paste it here. Please note that indentation is important in the YAML file, so let's indent it properly. We learned that labels are useful to filter the pods. These labels play a very important role in the deployments too. Let's say we have hundreds of pods. How does replica set know what pods it should manage? So in our replica set, we should give what labels the replica set to match. We give that with match labels and app as nginx. For simplicity, let's add the same labels onto the pod as well. So now replica set checks the pods with these labels and make sure 3 pods are always up and running with these labels. You might be wondering, why do we need to specify the labels in both places, in the match labels and in the pod specification? This is because the replica set not only manages the pods created by this replica set, it also takes the pods which already exist into consideration. Meaning, if a pod already exists with this label, it creates only 2 pods, not 3. It always makes sure the number of replicas are always available with the given labels, no matter how you create it. And these match labels should be under selector. Perfect. Now our replica set configuration file is ready. Let's change the pod name to nginx pod and let's correct the file name as nginx kubectl apply-f and file name. Awesome. The replica set is created. Let us verify if the replica set is created. kubectl get rs. Rs is the short name for the replica set. You can use rs or replica set. It doesn't really matter. As you can see, the replica set is created. And this is the name of the replica set we given. This column displays the desired number of replicas of the application. And we defined this with replicas attribute in the replica set specification file. The current column displays how many replicas are currently running. And ready column displays how many replicas of the application are available to the users. The reason why it is showing 2 is by the time we ran this kubectl get replica sets, the pod is not yet ready. If we try to run the same command, it should be ready. As you see, the 3 pods are currently available to the users. Age displays the amount of time that the application has been running. Now if we list the pods, kubectl get pods, the 3 pods are running and each pod has a prefix of the replica set name, which means these pods are created by the replica set. As we discussed, when a pod goes down for any reason, bringing it back is called self-healing. To mimic this, let us try to delete a pod and see if replica set can automatically spin up another pod. kubectl delete pod space pod name. Enter. The pod is deleted with this suffix. Let us try to list the pods now. As you see, still we have 3 pods even though we deleted 1 pod. This is because replica set always makes sure the given number of replicas available all the time. Now let us try to delete the node and see what happens to the pods. Before that, we should add another node to our cluster as we have only 1 node. Let us try to list the nodes we have. kubectl get nodes. As you see, we have only 1 worker node available. Minikube node add -- worker, and this is in the local cluster. Cool. Now the node is added to our cluster. Let's verify that with kubectl get nodes. As you can see, we have 2 worker nodes running. So before deleting the node, let us try to see on which node the pods are currently running. kubectl get pods -o y. Currently the pods are running in the local cluster M02 node. Now let us try to delete this node. Minikube node delete node name -p local cluster. Please check out the Minikube chapter of this series on how to manage the Minikube cluster. Let us try to delete it. Now let's try to list down the pods. As you can see, the pods are automatically recreated on a running node, which is the local cluster M03. This is how we get high availability. So far we have seen how self-healing and high availability can be achieved with the Kubernetes with hands-on. Now let us see how we can do rollout and rollback in Kubernetes. Let's say our application is running with the 1.21 version. If we want to upgrade it to 1.21.3, it requires starting the new version of pod, stopping the old version of pod, waiting and verifying the new version has been launched successfully. Also, there will be the case of rolling it back to a previous version in case of any issues. If we do this manually, there will be a lot of chances of errors and it's time consuming. We can automate this rollout and rollback with the deployment object in Kubernetes. When we create the deployment, replica set is automatically created. So no need to create the replica set manually. Every time we create a deployment, the deployment creates a replica set and replica set creates the pods. This is the reason pod is considered the smallest unit in Kubernetes. You might be getting a question, why pod is the smallest unit, why not container? Because container lives inside the pod. Container alone cannot be deployed to Kubernetes. Container must go with the pods. So that is the reason pod is considered the smallest unit that can be deployed to Kubernetes. However, replica set can be created separately without deployment, as we discussed, if we don't care about rollout and rollback and just want our desired number of replicas are always available. Let's see that in action. Let's go back to VS Code and create a new file, nginx-deployment.yaml. The deployment file looks similar to the replica set as of now, except the kind, which is deployment. And let's change this replica set also to be deployment, and we are good. And again, the difference between replica set and deployment is replica set always makes sure the desired number of replicas are always available, whereas deployment gives many more advantages over replica set, which are rollout and rolling updates, and we can give the deployment strategies, etc. Also note that whenever the deployment is created, replica set is automatically created. So no need of worrying creating replica sets manually. So before running this file, let's try to delete whatever we have so far with kubectl delete all -all. All refers to the all resource types such as pods, deployment, services, etc. Whereas -all is used to delete every object instead of specifying each resource name. Let's hit enter. As you can see, all the pods are deleted. Also, the replica set is also deleted. Let us see if everything is deleted with kubectl get all. So this will list out all the resources that we have in the Kubernetes. Don't get surprised why this pod is not deleted. This is in the terminating state, meaning it will take a little time to go away from here. Also, this is the default service created by Kubernetes and cannot be deleted. Let's try to run the same command to see if that pod has gone away. As you see, the pod is not here anymore. Let's clear the screen and try to run our deployment file with kubectl apply-f nginx-deployment.yaml. Enter. The deployment is created. Let's try to list down the resources we have. As you can see, 3 pods are created because in the deployment file we given the 3 replicas. Also, the replica set is created as we discussed. Whenever deployment is created, a replica set is automatically created, and that we can confirm with the prefix of the replica set, which is nginx-deployment. Also, the deployment is created. This is the name of the deployment, and here it shows the how many replicas are available to the users. This is 1 because the other 2 are in container creating state, meaning the container is not yet created. It takes some time to create those containers. And this shows the desired number of pods, which is 3, and up to date displays the number of replicas that have been updated to achieve the desired state, and available displays how many replicas of the application are available to the users, and age displays the amount of time that the application has been running. So now let's try to run the same command to see if the pods are up. As you can see, all the pods are in running state. And let us see if the pods have got the appropriate labels with kubectl get pods -show -labels. As you can see, nginx label is added to the pods as we listed in the deployment spec file. And this is the label that has been added by the Kubernetes. So if you want to scale our application, meaning if you want to increase the number of instances of our application, all we need to do is increase the number of instances here as 4, or if you want to scale down, you can change it to 2 and just apply the changes with kubectl apply-f nginx-deployment.yaml. Let's try to list down the pods now. Now we should have 2 pods running instead of 3 because we mentioned replicas as 2 in deployment spec file. As you can see, 1 pod got deleted. This is taken care by the replica set, which has been created automatically when we created the deployment. We can also scale the application with kubectl instead of changing the deployment spec file. That can be done with kubectl scale -replicas as 4 and our deployment name, which is deployment slash nginx hyphen deployment. So this is the resource type and this is the resource name. Enter. The output is saying that the deployment is scaled. Let's try to list down the pods now. Now we should have 4 pods and those are running. We must be careful using the kubectl for making any changes, as the spec file will not be the same as what we have in the cluster. For example, in this case, we have 4 replicas running in the cluster, and in the spec file, we have only 2 clusters we mentioned. So this creates kind of ambiguity. So it's always advised to make changes in the spec file and apply the spec file using kubectl command. Now let us see how rollout and rollback works in Kubernetes. Now we have latest version of Nginx is running. Let's try to change the version of this Nginx to 1.21.3. Now let's apply the file and see what happens. Let's clear the screen and apply. Now the deployment is configured. Let's try to run kubectl get all. As you can see, we have still 4 pods running, but if you look at the replicas, a new replica set is created. Whenever we change anything in the template section, it will trigger a new rollout. And when there is a new rollout, a new replica set is created. The old replica doesn't get deleted because when we want to roll back to the previous version, the same old replica will be used. By default, Kubernetes stores the last 10 replica sets and lets you roll back to any of them. Of course, this limit can be configured in the deployment spec file. We can also change the version of our application with kubectl command. Kubectl set image deployment slash nginx deployment container name nginx 1.21. So now we are changing the version from 1.21.3 to 1.21. Note that this is the container name. This is because a pod can have multiple containers with different images. So we should specify in which container we want to apply this image. So let's try to run this. The image is updated. Now let's try to list down the resources. kubectl get all. As you can see, we have still 4 replicas running, and we can check if the image is updated or not with kubectl describe pod. As you can see, the image is 1.21 version, meaning it is updated. As we discussed, it's always safe to apply the changes from the spec file instead of changing from the kubectl command. This is just to demonstrate we can also do the same thing with the kubectl command. So let's clear the screen and list down the history of the rollouts. We can do that with kubectl rollout history of deployment slash nginx deployment. As you can see, there are 3 revisions for this deployment. First revision was the initial deployment. Second deployment was when we updated the latest version to 1.21. Using spec file. The third revision was updating the version from 1.21.3 to 1.21 using kubectl set image. It's always a best practice to give the change cause, because now we don't know what revision is what. If we give the change cause, there will be a record of what has been changed. We can do that with record flag. Let's try to change the image again from 1.21 to 1.20 and hyphen record. So now the change cause will be recorded as the command that we are running. Let's hit enter. And note that this flag is getting deprecated. So now let's try to list the history of the revisions. As you can see, the change cause has been recorded as the command that we ran. But as a best practice, we should always specify the change cause using annotations. We can give the annotations with kubectl command, also with the spec file. Let's go with spec file and give the annotations in the metadata section. Annotations, and in that the annotation for the change cause is kubernetes.io slash change cause, and the change cause is updating to Alpine version, and let's change the image version to Alpine. Now let's apply these changes. kubectl apply -f nginx-deployment.yaml. It's configured. Now let's check the history of revisions. As you can see, this is the reason we have given for this revision. So this is how rollout works. We can upgrade our application at any point of time. Let's say after this rollout, we found some issues, roll back to the previous version. That we can do with, instead of history, we should mention undo. Now this will roll back to the previous version of the deployment, which is using 1.20 version. Or else we can give the specific revision number with 2-revision is equal to 1. Now this roll back to the first revision, which is using latest version of the Nginx. Hit enter. As you can see, it's rolled back. We can check the rollout status with kubectl rollout status deployment / nginx-deployment. As you can see, it's waiting for the deployment to finish. 3 of 4 replicas are updated, and finally it is successfully rolled out. So kubectl rollout status is used to check the status of the rollout. Now let's try to see if it is rolled back to the latest version by listing the pods and checking the pod image. kubectl describe pod name grep image. Oh, I'm sorry, we should give the resource type, which is pod. As you can see, it was pulling the latest image and successfully pulled the latest image. So that's all about self-healing, high availability, rollout and rollback. My name is Pavan Elthepu, and I thank you very much for watching this video. If you liked it, please share it with your friends and do not forget to subscribe to my channel to not miss any updates.